Swayam Prabha. Digital India. Educated India.
So LAMMPS uses its own language to define the simulations. So in what we're going to do, it will always start with the same information here, which is that we're going to use what they call the metal units, which are angstroms, picoseconds, EV, and bar for pressure instead of megapascals. Don't ask me why they didn't use megapascals but bars. It's their choice. Atomic means that there's no charges on the atoms, for example. And I have to say that I'm not sure what that does, but if you don't, it crashes. So I hide it without thinking too much. These are the boundary conditions. And so as we said this morning, we have to use periodic boundary conditions as much as we can. So here, the P means periodic in X, Y, and Z. And then here, this is where you create an FCC crystal. Basically, you tell the code that you want an FCC lattice with the FCC keyword here. This is the initial lattice parameter, the 4.1 that you have seen. And this is saying how many unit cells you want in X, Y, and Z. So here is from 0 to 1. So you have 1 unit cell in X, 1 unit cell in Y, and 1 unit cell in Z. Then here you import the potential file. So we're using one of the aluminum files. I used this one with magnesium also. So it's a binary potential because if some of you want to add solutes and see what it changes, you can do it readily with that potential. And so here it's going to run a minimization, but when you minimize, so you want to reach an equilibrium configuration. Obviously, numerically, you will never be exactly at the minimum, so you need thresholds. And so you know that when you're at the minimum, the forces on the atoms have to be 0. They're not going to be exactly 0, but you can put a small threshold, and the threshold is this one here. It's this F max that I defined to be 2.5 10 to the minus 5 EV per angstroms. So that's small enough that you are close to the minimum. And then we want both to minimize the positions and also change the simulation cell size to be at 0 pressure. And the 0 pressure is set here. So with this box relax command, we say that we want to relax the simulation box. The ISO says that we want to relax X, Y, and Z of the same amount. So the cubic cell will remain cubic. And the 0 is the target pressure. Since it's ISO, there's only one value, it's the pressure. We say 0, and there's a threshold, but it's an internal value chosen by LAMMPS. We don't, at least here, we don't change that threshold value. We only play with the value for the forces. And then we do the minimization, which is here. So LAMMPS so there are 2 criteria to stop the simulation. The first number here would be a criteria in terms of how much the energy changes one step to the other. But actually, that energy variation is not a good criterion. You can be very far away from the minimum and for some steps have a very small energy variation. So I always put 0 here, not to look at the energy. And I only look at the force criterion, which is this F max value that we have put above. And then this 10,000 here, this is the maximum number of steps that the minimization will do. So if it reaches 10,000 steps and hasn't minimized, it will stop. And then this is just to report, it's just to compute the pressure and so on. This is to give you give you some data about the simulation. And the line I forgot is to write the relaxed configuration, right? So if you run it, what it does is, so it creates the crystal, blah, blah, blah. What I just want to show you is, is this line, is when it does the minimization here. So I asked it to tell me what is the step number. So here would be 0. Then this is the force on the atoms, the maximum force on the atoms. And here, because we start with, even if the lattice parameter is not correct, the atoms are on symmetrical positions. And so the force is 0. The force on the atoms is 0, but not the pressure in the cell. So it's going to minimize even if there is no force on the atoms because the pressure is not 0, which is the target pressure. So the force is 0. This is the potential energy. And this is the size of the cell, so the size of the size of the unit cell in X, Y, and Z, and it's 4.1 as we have said. And then here, these are the pressures. And so what we see is that here, there should be a number, wait a minute. What did I write? PXX 4.1, there are zeros everywhere. There should be a big number. Why is it so small? Anyway, let's forget about it. This is a detail. But what is important is here. If you look at the lattice parameter, it starts at 4.1, and then it's going to change, step by step. You see that the lattice parameter decreases, 4.08, and then it goes down and down and down until it finds a position here where the pressure is small and the lattice parameter is now 4.32. And that's it. It's the end of the simulation. And so then it just repeats. So these are just comments from LAMMPS. In the end here, it just repeats. This is the lattice parameter it found, 4.32. The internal pressure in megapascals, so you have to check that it's indeed small. And then you have the cohesive energy, which is here, 4.36. So that's the energy per atom in the reference configuration. Is that clear for everyone?
How many total atoms were there?
So here it's just one unit cell. So how many atoms? 4. Yeah, for FCC. It's going to be just 4 atoms.
That's it.
Because it's just the smallest possible unit cell. Now, Anand told you to play with the lattice parameter. So I know that if I go very far like this, I don't know. You tried and it seems that something happens if I put 5. So let's see if, so here, no, with my code it works actually, 5. Too bad. Because one of your colleagues started with a very large lattice parameter, and with his version of LAMMPS, it did not converge. The conjugate gradient did not converge, and actually, and you can see if it does not converge, you can see it on this line here. So here it says that the conjugate gradient stopped because it had reached the force tolerance, so that's fine. In his case, it was written line search failed or something. There's line search alpha failed or something. And this means that the conjugate gradient got lost in its minimization. So that's where you have to be careful that the minimization was not done properly with the LAMMPS. And we can talk about that later on, but what you usually do then is you alternate between LAMMPS and fire to reach a real minimum when LAMMPS is, you alternate between conjugate gradient and fire. You alternate between the two. To properly converge your simulation. So the force max will be it's the maximum component so in any component x, y, z of any atom. So it's a measure of the magnitude of the vector, of the force vector of the system. Now we can look at it by using Ovito. So Ovito, and then I plug the. So this you have all seen, right? So here, if I go like this is my unit cell where I have one atom in 0, 0, 0. And then I have one atom at the center of the left face, one at the bottom face, and one in the front face. And then if I repeat that simulation, that cell, so to repeat, with Ovito, you have this, so with Ovito, you have this add modification where all the tools are. And if you go down, there's one which is called replicate. And so if, for example, I replicate by 10 in X, 10 in Y, and 10 in Z, and 10 in Z, up, that's it. Then I have my perfect FCC crystal. So looking at a very small unit cell or doing the calculation on this big cell would not change anything because we have a perfect FCC crystal. That works?
So here also the surface, because there were only 4 atoms in the simulation, the surface effects were taken care by the
by the periodic conditions. Exactly. Yes. Actually, we can do the test. We can do with the because of the periodic boundary conditions. It's exactly the same whether you're using 4 atoms or more. So we can check that actually. We can go, where's my thing here? So I'm going to go back to 4.1, and then I go, for example, from 1 to 5, 1 to 5, 1 to 5. So it's going to be 25 times slower, still fast. So here, because it's 5 times bigger, it's no longer exactly what we expected. We have to divide that by the number of unit cells to get back to the same value. We have the same cohesive energy, 3.36, and the pressure is still very small. And if I use Ovito again directly on that 5 by 5 by 5, this is the cell that Ovito minimized. So now, how do I compute the formation energy of a vacancy? For those who have looked and the others, how do I compute? So I have aluminum. Now I know that my potential predicts a lattice constant. This would be 4.032, right? And the cohesive energy of 3.36. Now, I want to look at defects. And so the first crystalline defect that I want to look at is a vacancy. And so a vacancy is an atom missing from the crystal. And I want to compute what is the energy of a vacancy. How much energy does it cost to create a vacancy in the crystal? So what I want to do is take 1 to infinity, or just I want to remove 1 atom. So we have our simulation cell, which is here. And what we do is we take out 1 atom. So we have a hole here. So we have, if initially we had n atoms, now we have n minus 1 atom, right? And with the because of the periodic boundary conditions, there will be a vacancy here, and then here, blah, 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 everything around, right? And that will lead to size effects, because these vacancies will all interact. And so if I do the calculation for different cell sizes, the interactions will be different, and the energy I will get in the end will be different, and that's the size effect, right? But now so imagine that, so I take that cell and I do an energy minimization, and I'm going to get an energy. From the energy that I compute, how do I get the energy of the vacancy? Because the energy that I'm going to get is the energy of the full cell here. It's the energy of these n minus 1 atoms. So how do I now extract the energy of the vacancy itself? Yeah, but what is important is the cohesive energy for how many atoms?
Less than 1.
Less than 1, right? So the formation energy of the vacancy, it is the energy of a cell with the vacancy, so n minus 1 atom, minus n minus 1 times the cohesive energy. You always have, when you compute the energy of a defect, you always have to be careful that you have the same number of atoms in both cells. Otherwise, you have a cohesive energy difference that's gonna be around, right? So, and this one, if you want to do it, you can do it in a different way. So the cohesive energy is just the energy of a perfect crystal divided by the number of atoms, right? So you could also do n minus 1 divided by n times the energy of a cell with n atoms, right? If you take that cell, you minimize it, you have the total energy, you divide by n, that's the cohesive energy, you multiply by n minus 1, that's the cohesive energy of n minus 1 atom, and then minus the energy with also n minus 1 atom, and then you get the vacancy formation energy. Yeah, so what you want to know what is the difference in energy between n minus 1 atom with a periodic cell and the energy of the same n minus 1 atom, but in a perfect crystal. And the cleanest way, so this is just to do it numerically, but the cleanest way is that. So by definition, the cohesive energy, this number which is here, this is the energy that an atom has in a perfect crystal. So n minus 1 times this cohesive energy, this is the energy of n minus 1 atom in a perfect environment. And this would be what LAMS will give you is the energy of n-1 atom, but with a vacancy. And so the difference between the two is the formation energy of the vacancy. Yes? So how much did you, what's the formation energy in aluminum for that potential? It does not mean it's the exact one, but what did you find, those who did the calculation? I know some of you did it because I've seen the results. So how much is the formation energy? 0.68, yes. So to get there, maybe we can have a look at the, so this is the script to compute the vacancy formation energy. So the beginning is the same as always, metal, atomic, map hash, periodic boundary conditions everywhere. Now, so here, what changes compared to before? This is where I create the crystal. What did I change compared to before? So I'm starting with the correct lattice parameter. Now I know it's 4.032, so that I'm using it here. And the other difference is what? The size, yes. Instead of having just one unit cell, now I have 4 unit cells in X, Y, and Z. This is because of the, I mean, if I have just one unit cell and I remove one atom, the number I'm going to get is going to be completely crap, right? So this is 4 is just a number, small but different from 1. So I create a perfect crystal. I use the same aluminum magnesium potential. And then I do the same minimization as before, right? So the first result here is the same as before. And I do that to get the cohesive energy, which is defined here. I compute the cohesive energy. And then what do I do? Then what do you think? Sorry, it's written, but so LAMS has zillions of scripts or commands. So in this one, they have one command that allows you to remove one atom from a cell. So it's this delete atoms. So what I'm saying here is that, so with this variable middle equal this, so middle will be equal to so I have n atoms in my cell. So the index of the atoms goes from 1 to that number of atoms. And so n over 2 is the middle of the indices. And so I get middle as the index of just because I need an index of an atom. So just to take an index of an atom, I take half the number of atoms as a reference index. And then I say that I define a group, which I call vac, like vacancy, which is made of the atom whose identity is the number I got here. So this is just to select one atom. So I'm selecting one atom here whose index is half the number of atoms in the cell. And then I use this delete atom, and I delete the atoms which are in the group VAC, and VAC contains only one atom, so I'm removing just one atom in the simulation cell. Do I make sense? Yeah? And then I do an energy minimization again. So this hasn't changed. I do again, sorry, it's here. I do again the minimization. And then here I apply the same formula as here. So this is in LAMS terms. I had to define variables. So this is the total variable the total energy in my n-1 cell. And I subtract the cohesive energy multiplied by the number of atoms, which now is n-1 after this minimization. So this is exactly what we wrote together. And then I write the energy. So if I run the calculation, so LMP serial minus in dot vacancy aluminum. Everything goes super fast. I get 0.68 as you found. Now here I didn't forget the right data, so I can do Ovito, and I guess it's relax. So this is the crystal. It looks a bit ugly with atoms, but this is because of the periodic boundary conditions and atoms near the boundaries. If I replicate the system, the system will look much better. So here there are still some atoms, but here inside you see that it's a perfect crystal. So the atoms that we see on the sides are just because they are moving through the periodic boundary conditions. How do we see the vacancy? I was about to do it. So there are different ways. If you go to the add modifications, at the bottom here, there are these structure identification things. And one that works well is called common neighbor analysis. And so if I do that, then I see, so for now I still see nothing. But then if I cut, I do a slice. So the green atoms, so what this common neighbor analysis tells you is that the green atoms are FCC atoms. And so I can put HCP, BCC, so here there's nothing that has changed. And there are these atoms that are found other. And why is that? It's because they are missing one neighbor. So if you look in the middle of this group of atoms, there is one missing atom, it's the vacancy. So the gray atoms are the first neighbors of the vacancy. So you see here we have we have a square lattice here, and with so atoms, and see atoms, and here there's one atom missing, atom. So this is where the vacancy is. So now you can do exactly the same, but instead of removing one atom, you can add one atom to the system. And that will create a self-interstitial. You can have a look at that. You can choose. You can either look at the self-interstitial, or if you want, you can look at the intrinsic stacking fault energy to look at see what it looks like. There's an input file that creates this stacking fault if you want to look at how it can be done. And yeah, this you want me to do. So you can choose either to look at the self-interstitial formation energy or the stacking fault energy.